If you're listening to this hint, I'm guessing that you've figured out what the first derivative is accurately, but for some reason are having trouble working with the second derivative to determine the concavity of our rational function. Since the first derivative is a rational function, we're going to need to use the quotient rule in order to take its derivative, and we're going to have to be very careful with our algebra. That might be the thing that's tripping you up. If so, practicing this sort of algebra would be a really helpful thing for you to do. To use the quotient rule, we start off by taking the derivative of the top, which is just a minus 2x. We leave the bottom alone, and then we subtract off the top times the derivative of the bottom. And in computing the derivative of the bottom, we're using the chain rule. All of that goes over the bottom squared. We notice on the top that we have a negative 2x and a 2x with a negative sign that we can factor out at the top. We also notice there's an x squared plus 1 showing up in both terms on the top as well as on the bottom. And so we can factor out an x squared plus 1 from everywhere, cleaning up our expression just a little bit. All of which leads us to this slightly simpler equation, which just gets neater when you work through what's inside those square brackets, and you finally end up with 2x times the quantity x squared minus 3 over the quantity x squared plus 1 cubed. Now that we have a nice expression for the second derivative, we need to use it to figure out what the critical points are for the second derivative and then determine where our function's concave up and where it's concave down. I'm going to figure out the plus-minus chart a little bit differently than in earlier examples, just in case the difference is helpful to you. I'm going to look at the constituent pieces and then glue together the information from each of those pieces. So for example, 2x is part of what makes up the second derivative, 2x is positive when x is bigger than 0, and negative when x is less than 0. Similarly, x squared minus 3 is positive bigger than root 3 and positive less than negative root 3, but it's negative in between. And x squared plus 1 is always positive. To figure out the positive and negatives for the second derivative, we then just need to look at how the pieces multiply together. So if we're looking at values of x that are bigger than root 3, we know we have a positive, and a positive, all being multiplied or divided together, and so the grand total answer is going to be positive. Similarly, if we're between 0 and root 3, we have a positive, a negative, and a positive, so that's going to be negative. Between negative root 3 and 0, we have a negative, and a positive. Two negatives make a positive. And finally, below negative root 3, we have a single negative and two positives. That'll be negative. And so we sure indeed do have a point of inflection at each and every one of those points. And we're going between concave down to concave up, concave down to concave up.